In this video, we discuss the binary pulse precision modulation. This is an example here. We use this waveform to represent digital bit 1 and use this form to represent digital bit 0. We can see that this pulse sitting at from 0 to half TB, and this pulse sitting at from half TB to TB. And in the meantime, they have the same magnitude. So therefore, this modulation is pulse position modulation. The amplitude the same, so it's different than the amplitude modulation. In the amplitude modulation, the amplitude is changing. This is a digital 1, the waveform. The amplitude is A, and this is digital 0. The amplitude is minus A. But at the same time, they have the same shape of the pulse, has the same duration. Next, let's look at the geometric representation of these two pulses, S1 and S2. In this case, we need two orthogonal base functions here because we can see this is a pulse ending at half TB. This is a different time duration even. These two pulses are sitting at different time. One orthogonal base cannot represent two pulses at the same time. So we need two bases, and these two bases has to satisfy this condition, psi 1 of t and psi 2t, psi 2 of t. If we do integral from 0 to tb, that's the duration to transmit 1 bit information. We have to have equals 0. This defines the orthogonality of these two waveforms. I have it here. So if I have two waveform S1t and S2t, if I do product and do integral, that equals 0. They are orthogonal signals. And this S1t and S2t can be any signals. And by chance, in this case, S1t and S2t, they are orthogonal as well, because if we multiply them together, everything is 0. So we do integral a ended up 0 as well. S1t and S2t, these two pulses are orthogonal. Now, how do we obtain the orthogonal base from all of those pulses? There is a standard procedure called Gram-Schmidt orthogonal procedure. You start with the first waveform and you obtain phi 1, and then do projection, look at the residue, look at the next waveform and obtain the second orthogonal base. This procedure is not focused here. So we just pointed out that the orthogonal base for these two signals here, S1t and S2t, has the same shape, has the same time domain waveform shape as S1t and S2t. The only parameter is that we need to find the magnitude. We need to find the magnitude for this orthogonal base such that the energy content in this base, in the base function, equals to 1. Now let's look at what's the magnitude for psi 1. Here I call it the magnitude b. We do integral from 0 to tb psi 1 t d of t, that equals to, because you only have values from half tb, that's equals to half tb. That's a b squared d of t. We want this equals to 1. V equals to square root 2 divided by tb. That's exactly what we obtained here. So we do the same procedure for another orthogonal base. That's the magnitude we obtained. How do we obtain the coefficient? There are two base functions here. For each pulse, there should be two coefficients. One coefficient associated with this base function, the another coefficient associated with this base function. So written in the form is that this pulse S1t equals to a coefficient multiplied by psi1t, that's the first base, the second coefficient, that's S12 associated with second base. And for the second pulse, the coefficient associated with first base is S21. The coefficient associated with second base is S22. So we can see here, first subscript, that's the pulse index, and this one associated with the first base, and this two associated with second base. And the same thing here, the second signal, subscript 2 associated with second signal, and 1 associated with first base, and this 2 associated with second base. The coefficient for the first signal related with the first base, we do the integral from 0 to TB, and this we can calculate that equals to square root EB. Now I'm going to illustrate how do we calculate the coefficient S11. This integral of this waveform multiplied by this waveform multiplied by this waveform, and both waveform has a duration from 0 to half TB, so integral become rectangular, this multiplied by this square root 2EB divided by T, B multiplied 2 TB and D of T, and this equals to, this multiplication becomes to 2 square root EB TB, and you do integral to half TB, that's half TB, and this equals square root EB. For the coefficient S12, this waveform, we do this waveform multiplied by this waveform, and you can see the multiplication 0, so therefore S12 equals 0. We do the same thing for the second waveform. Those are the coefficients we obtained. Therefore, the geometric representation here is a vector here. It has 2 dimensions. This is a dimension of psi1 t. This is a dimension of psi2 dimension. Okay, the coefficient become a vector. This vector has 2 coefficients. This is for the first signal, first pulse, and this is for the second pulse. Become a vector. That's here.